finally, let's look at how we can use simulation software Simul8 to create an MCNQ. And again, we're going to use the example from the lecture notes. And to do that in the lecture, we have MM13Q, one server, total capacity equal to 3. And to make that possible, if you want to continue working on this particular example, I have to get rid of the last server. So you can single click on this and click delete from your keyboard, and that server is gone. Now you go back to this MM1Q again, and if you want to specify that the total system capacity is 3, this is where you go to the Q capacity. Before it's infinite, and here MM13Q means the Q capacity is 2. So 2 queuing capacity plus 1 server capacity give you n equals 3. Now with these being done, we can come back and change the parameters. Right here, the arrival rate is 2 per hour, the one we have before. The inter-arrival time in this case would be 30 minutes. This is our first example, actually. And the service time will be 20 minutes, so 3 jobs per hour. And of course, to make the calculation properly, we have to go to the properties, clock properties, and set this one accordingly. We use 60,000 minutes for the warm-up period, so 30 minutes per customer. 60,000 gave me roughly 2,000 customers in the warm-up period. For the results collection period, I use 300,000. Give me about 10,000 customers already. Okay, okay to confirm. And before running the simulation, there's one more thing I want to add. Remember in MCNQ, because the finite queue capacity, some of the customers arriving at the queue may be rejected since one queue is full. And to be able to calculate that, I have to go to the arrival block, which is my start point, click on results, and add something into the results matter. You see number of work items, enter the entry point, edit, number of work items lost, also edit, and the number of work items remainder of the remainder of simulation. Okay. So of course, if you want to calculate the effective arrival rate, lambda sub e, I need to use the last horn divided by the first node. Okay. The one entered the system divided by the total number created. I OK this, go back to Home tab, run trial. The results are done. Now let's compare the numbers. Now the theoretical number for the average queue length is 0.431 from the lecture notes, and here we have 0.43. And the average queue time we have is 0.246 hours. It's a quarter of an hour, a little less than a quarter of an hour, so it's roughly 15 minutes. So we have 14.84. So if I do the exact calculation, 0.246 hour times 60 minutes is actually 14.76 minutes. So it's very close to what we have here. Only less than 0.1 minute difference. Now, how do you know lambda e? Well, for Little's law, you will calculate it from what we have here. But it's also possible to calculate based on the numbers that we have seen in this column. For instance, if I want to know the average, the percentage of arrivals lost, apparently it's going to be equal to 1236.2. This is the average number of customers lost on average, divided by the one on top, the total number of enters of 9943.40. Do the calculation, give you 12.4%. The theoretical answer of the number of rival lost will be 12.3%. It's very close to the theoretical answers. If you want to know the effective arriving rate, it's going to be the total number of customers coming in, A707.2. Right, divided by the total results collection period. The results collection period is 300,000. And if you divide that into that, you'll be able to exactly find the number of customers arriving per minute, being 0.29 in times 60. Sorry, 0.029 and times 60 minutes, you have 1.74. So let me do the calculations here together with this. So we will find so 8707.20. This is the total number of customers arrived and remain in the simulation, divided by the total amount of time you have observed it, which, as we have seen, is 300,000. So 300,000 minutes. So 0.029024 customers per hour, per minute. If you want to convert it to per hour, times 60 minutes per hour, and give you 1.74144 customers per hour, being the effective arrival rate. And that is very close to the theoretical answer lambda e. According to the lecture notes, is 1.754. 1.754. So less than 0.1. Okay. So this example shows us how we're able to create an MMCNQ and how to calculate the performance metrics, the effective arrival rate, a loss rate of the customers, and other performance metrics as the other QA systems. Okay. So with this, you should be able to construct simulation models for the MM1Q, MMCQ, and MMCNQ. In the next video, we're going to show you how to create MG1Q, which is slightly more complicated since this general distribution have to be carefully selected and the parameters have to be calculated in a more rigorous manner. And we'll do that in the next lecture.